Guys, welcome back to another episode of Stonks Maxxing. This is day 78, part 10 of our Intel series. So what we're going to do in this episode is continue building out the client compute group segment. I think this is Intel's strongest segment. It's essentially the process of designing and manufacturing, more so the designing, I would say actually. Designing everyday central processing units, CPUs, for computers, think laptops, desktops, and maybe some mobile-ish devices like tablets or foldable on-the-go laptops. So Intel right now, just kind of a little background of where we're at. I think it's down 60% in the past year to date. And I just realized not even, okay. Hide OBS. There we go. So yeah, we are currently down. I say we. I mean Intel is currently down 60% since the start of the year. What happened, right? So I think maybe problems started to stem back in 2015, 2016. The company decided that okay, our Intel Core series of chips. This is pretty much a cash cow for us. We're going to try to stick with what we know and not really take any risk when it comes to mobile and even data centers as well. More so on the mobile side. I think Intel was pretty late to the mobile game, and this led to Qualcomm being pretty much the de facto standard of mobile processing units. So I think Qualcomm probably makes the Snapdragon series of processors that most phones use today. I think those are more system-on-a-chip type processors where you have, let's say, a central processing unit, a GPU, and also some RAM on a single chip, and then it kind of does everything you need. Because with a phone, it's slightly different from a computer. First of all, the actual size of the phone is a lot smaller. And then I think in terms of receiving calls, there's maybe a cellular modem that you need as well. And then the audio system is different. I think the way that you receive data from your cellular service is slightly more complex. So those are all things to think about when it comes to mobile, specifically smartphones. But going back to 2015, Intel decided mobile wasn't really good enough for them. It was too much of a risk, so they decided against it. I think also EUV, that was a big part of TSMC's strategy. They took a big risk back, I think in 2015, 2016. It should be good to confirm that. On EUV, which is really the next generation of I think hey, some good things happen. I heard something upstairs. Let's go. Okay, so I hope that happens with Intel. I hope we can make that sound one day. But what I was thinking is this, right? TSMC, they ended up taking a big risk on this EUV stuff, and it worked out. I think today TSMC is on their 3 to 5 nanometer process. What does that mean? It just means that they are creating the cutting edge chips. They have the ability to make, I think, the smallest transistor size. If you look at the gate of a transistor, it's not exactly 3 nanometers, but it's around 50. So around 45 to 50 nanometers, which is already really fucking small. I think that's a piece of hair, right, is 100,000 nanometers. I think the mitochondria, the powerhouse of the cell, is around maybe, I want to say maybe like 60 to 70. Let's see. Mitochondria. NM, right? 200 to 500 nanometers. So a single transistor today, size 3 nm process. 56 nanometers. Shoot, dude. So that yeah, it is smaller. It's about 10 times smaller than a mitochondria. Okay, that is kind of crazy. So these transistors, what do? They pretty much act as switches, right? They just switch a circuit on and off, and on essentially is 1, off is 0. It's kind of like this abstraction of how data is stored is just in binary ones and zeros. This is important because all of the processing that happens on a processor, I think that's just electrical current flowing through a circuit, and these transistors will somehow, using instructions, turn on and off and let data and information to flow through. Yeah, that is my best sort of crash course on technology. But EUV was important. So I think EUV, if you look at the manufacturing process for these chips, there's really 8 key steps according to branch education. All of this starts with a single circular silicon wafer that's about 300 millimeters. And I think today you can fit about 100 or so CPUs on that. So you have this circular sort of die. Sorry, it's a wafer, not a die. But you etch these dies on top. This is probably a good point to pull up my notes because I don't fully remember everything here. Yeah, let's go to semiconductors. Okay, yeah. So this is what a central processing unit. So integrated circuit, die, or chip, these are all pretty much the same thing. It's just all really jargon in the industry. These are cores. So each CPU has, I guess, different sections that are used for different purposes. The cores here, I believe, are actually used for the information processing. And then you also have things like the memory controller, which will allocate the different bits between each register, I believe. And you also have, in this case, a GPU. So I'm surprised to see this on the same chip. You also have compute fabric. It's PCI 5.0 lane. I think this is at the actual motherboard. I'm not entirely sure. There's some stuff here that I definitely don't fully understand. Oh, right. So each CPU, this is actually pretty key, right? 2 fundamental basic elements of a microchip are interconnects and then transistors. So the interconnects are these microscopic metal wires. And transistors are the switches here. I think these are FinFET transistors that just denote this gated sort of layout. And then there's insulating material on the microchip that provides structure for the interconnect wires. Yeah, so it's kind of like a highway, actually, the whole interconnect thing. You have transistors that sit at the bottom of your CPU, but then you have these sort of layers on top of layers of interconnect. And if you look at this, you have multiple cores, right? So I think you have local interconnects that will span this region and be able to transfer data locally. Then you also have, I guess, regional interconnects, which maybe the 4 cores here are all connected through a singular interconnect system. And then you also have this global interconnect, which connects the whole CPU together. So what do? I think copper is just sending signals, electrical signals. Copper is I was about to say semiconductor. It's a conductor, right? It's a conductor of electricity. And this allows these electrons to flow through. Yeah, there was an interesting thing that was brought out. It's like, okay, how small can these transistors really get? Because can they get to like the size of an atom? At that point, I mean, is that even possible? Versus maybe even the size of an electron, right? An atom is composed of what? Like a proton, a neutron, and an electron. You also have the outer rings of an atom. I think the outermost ring is the valence ring, or the valence shell. Then you also have electrons on the outer shell, which are the free electrons, the valence electrons, those are the actual electrons in an element that you can sort of flow through a circuit. Yeah. Okay, yeah. So this is where I got the mitochondria thing. Alright, the mitochondria is actually a lot bigger than what a transistor looks like. Okay, so this is a good analogy. Making a microchip is like baking a cake, except the cake is really big in terms of size, and it's super tall. There's 940 steps and has hundreds of exotic ingredients, and it takes about 3 months to complete. Alright, so making a microchip. This is kind of like a noob overview, but I believe there's 8 steps here. So there's oxide deposition, photoresist spin coat, photolithography. This is where the EUV comes in from ASML, where TSMC took that big risk. Photoresist etching and photoresist removal, metal deposition, and wafer planarization. Okay, so I think first thing, oxide deposition. So what does this mean? I think this really just means you're adding some chemical elements that have an oxygen chemical compound. I think oxide just means that an element that contains a singular oxygen compound or a single oxygen element. So you do that first. So this is essentially spraying and depositing layer of silicon dioxide on interconnect layer. This is to, yeah, not too sure what that does, but apparently that's, so photoresist spin coat. So photoresist is the idea of some type of material that tends to interact with light, or when you expose light onto it. And so usually what happens is when you're making a semiconductor, what you'll do is you'll have this wafer right here, right? Or this layer of interconnect. You'll deposit some type of insulating material. That's what this is right here. And then you'll put on some photoresist and then shine the EUV light onto the photoresist so that I think you do then some type of light shining on the photoresist to make that photoresist dissolve or go away. Yeah. So you also put on a type of mask to prevent the circuit or certain parts of the photoresist from actually going away. Etching will go all the way to the interconnect layer underneath. How do you know when to stop, right? Just stop. Okay, so that's, repeat this 80 times. Ooh, yeah, this right here is a tough one. Yeah. maybe I'll save this going deep into the details for another stream, because we're already going over some time, but exactly what happens here, all of these 8 steps, really 940 steps, happen in a clean room. And so the clean room is pretty much a room that is super secured and super clean, because a single dust particle is larger than a transistor and can fuck up a complete integrated circuit. Oh, so 230 chips nowadays. Yeah, that's a lot more than I originally thought. But the fab, right? I think when it comes to moving things around, everything is moved or transported using a FOUP, a front opening universal pod. How do you increase the production capabilities of fab? Essentially, you just build a shit ton of these machines or maybe not build, but at least buy them and stack them in kind of like this assembly line fashion to be able to increase your output, right? Mask layer, so adding material, removing material, modifying material, cleaning, inspecting. So these are the sort of 6 different types of materials, or I guess categories of tools that are used. Mask, adding, removing material, modifying material, cleaning, and inspecting. Okay. Yeah, so this is about as far as I got deep into the actual process. I still need to finish the branch education video because that was really helpful. But going back to the strategy, TSMC took a big risk, paid out. They can make cutting-edge chips now. If you look at the landscape of chip designers, AMD, NVIDIA, Qualcomm, Apple, all of them are using TSMC. No one is actually using their own internal foundries. They're all outsourcing that. So I think this means that, 1, these companies have very little CapEx spending. They don't need to build big factories like Intel. They don't need to spend millions of dollars on an advanced extreme ultraviolet lithography machine. They can just ask, I guess, TSMC to make a chip for me. But I think when you look at the margins then, I'd imagine that gross margins for most of these chips designers are not that strong if they're depending on someone else's supply chain and someone else's manufacturing capabilities. If you look at NVIDIA today, their gross margins hover around 70% though. So I think NVIDIA is in this unique position where, sure, they're outsourcing their production, but their products are so high quality. Their H100s, H200s, and Blackwell GPUs are so advanced compared to any of the other chip designers. I think Intel is trying to promote their Gaia system, or Gaudi system. Yeah, their Gaudi AI accelerator. But NVIDIA, they are definitely top dog here, and they could command a price premium over their peers. So I think H100s, if you bought one of them, it'll cost you like $20,000 for a single cluster. Yeah, that's a lot of money. I don't even think it probably costs more than, 70% of 30% of 20,000. That's like 6,000 to make. So yeah, maybe like 5,000, 4,000 at most. I don't know. That could be something to look into. So yeah, that's really interesting. I think when I looked at Intel today, what I'm still excited about is their client compute group. So that's where I guess this is where I should probably start talking about now, and where we should continue our stream. Client compute group, I think we had said before, they make everyday computer chips for desktops, laptops, and other sort of devices, mobile devices that are still sort of like PCs, personal computers. Intel is pretty much the leader in this space. You have competition from AMD. You also have competition from Apple internally, and also Qualcomm with their new Snapdragon. AMD, I think, is their Ryzen series of CPUs, but mostly today, I think everything is x86, and the actual underlying technology behind it. What really matters here, I think, is sort of the instruction set architecture behind each processor. Intel and AMD both use the x86 instruction set. So what is this instruction set architecture? I think what this really is, it's a set of instructions, kind of like a language that your processor can actually read. And the x86 is just another language. I think another big one is actually the ARM instruction set architecture. And maybe even MIPS. MIPS was a big instruction set architecture back maybe like 2005-ish, around that time. But this is really important because actually the software that you write really depends on the underlying instruction set architecture that you're using. So if you're, let's say, using an Apple computer, right, versus a Windows computer, the Apple operating system is Mac OS. The Windows operating system, I think, is Windows 11, Windows 10. something like that. Under the hood, there's really complex programming that needs to work on the underlying hardware. And that involves an assembly type language where you can translate a lot of your computer code, so think Python, C, into machine code, which is just binary zeros and ones. And assembly language really is the underpinning language behind every, let's say, higher level abstraction of assembly. So Python, JavaScript, C, Java, all of these are high level abstractions of really the instruction set architecture for each processor. So what is the job of the instruction set architecture? Like, what are some instructions you can do? This is really super granular. Essentially, you're just moving bits around, bits of data. Everything is just stored in these little bytes on either your memory or your CPU registers. And you can just pretty much add, subtract, multiply, shift bits in order to get data moved from one register to another, and somehow that ends up changing some type of, I guess, front-facing application on your computer. So if you're using x86 versus ARM, you're going to have to completely rewrite your operating system in order to work on this ARM chip. And also, you're going to have to completely rewrite all of the software applications that you've downloaded. Now, I think from, let's say, a technical perspective, this could be possible if more things become web-based. So I think previously, a lot of applications were sort of downloaded directly onto your computer. Today, most things are web-based. Like, you can just go onto a website, let's say Google Docs or even Microsoft Teams. You could access it over some type of internet browser. You don't need to do everything on your device now. You'll have AWS hosting, let's say, billions of these applications on their servers. You can just send an API request and they'll fetch it for you, serve it onto your browser. So that is like one technical risk I can see. But in terms of, let's say, x86 versus ARM, I'm still a big believer in x86 and their ability to get us sort of like strangle the PC market. Another risk I could see is, let's say Apple is doing this right now with their Mac OS. They're creating their M1, M2, M3, and M4 ARM-based chips. I think what's different with Apple is that they actually have complete control over their operating system and the distribution of their operating system. They're not like Windows, where they essentially sell their operating system to different types of OEMs, think Dell, HP, Lenovo, Asus. Apple sells Mac OS only to its Mac products. So they have complete control over, one, the distribution, and two, the technology. And if that's the case, then they have complete control over whether or not they can make this shift from x86 to ARM. And it seems like, from what I've seen online, people actually really enjoy what has gone on so far with this x86 to ARM shift. I think most people using Apple products don't actually play games too much. When it comes to ARM-based chips, they're not really useful for gaming because of their reduced instruction set architecture. There's not as much, let's say, abilities, or there isn't as an advanced way to interact with the computer as opposed to the complex instruction set computer architectures, so this is, which x86 is. And I think the good side is ARM does have a lot of energy efficiency when you're using these reduced instruction set computer architectures, because there are less instructions that your CPU needs to process, and so there's a lot less bloat.
Yeah.
Yeah.
All right, so can you still do it a little bit?
Yeah.
Let's go.
Okay, perfect.
So I'm meeting with her, but let me just, I'll see you by the office.
Yes,
5 minutes?
yes.
5 minutes.
Yeah, give me 5 minutes. Perfect.
Thank you.
Okay, so I think with that then, let's dive into some of the recent financial performance. So I think what we've seen in the past, let's say 2-3 years, if you look at ASPs, okay, let me copy this. But essentially, you'll see here that PC sales have actually been declining. Wait a minute. Yeah, why is this 2016? Not entirely sure where this is coming from. Yeah, I fucked up some of the formatting, but what I wanted to show here was that PC sales actually started falling a lot in 2021 and 2022. I'd say mostly 2022 actually. This is a 10% increase. 2022, 2023, and maybe even 2024. So you'll see that past years, shipment volume has been declining. And so that's been flowing over to Intel's revenue, top line growth. And Intel has faced declining revenues in the past 2 years, 3 years really, starting from 2022 all the way up until 2024, which they actually saw, I think, increasing revenues. Let's see. So if we do quarter over quarter, percent year over year. Maybe it'll be nice to see like a rolling average of sorts, so you can kind of smooth things out. But let's take divided by -1.
Okay, perfect.
-1. Okay. Did see a slight quarter over quarter. Yeah, so it does seem kind of cyclical-ish, maybe? No? Okay, so Intel 10Q 2023. Let's do that. Thank you. Okay, not too sure what that does. Can I get a PDF version of this? Nice. Okay. Second, trends and results. So 24. Okay, client compute. Alright, so we have this breakdown again. 3 months ended September 2023. So this probably would be, yeah, this would be October 1st around Q3 then. So 2753 4503 6611. Okay, so yeah, that is a pretty stark year-over-year decline. Data center and AI. So you do see it's pretty operating income. Shoot. Operating income, so 3222 data center AI. Client computing 2077 1447. So you did see operating income actually increase 2023. Okay. 2073. Alright, nice. And 2023 Q4 data center AI. Yeah, I'm gonna skip that for now. Let's take a look at just the 2023 10Q Intel. Oh, maybe this. So they're missing something. Probably they missed because of some type of restructuring that they were doing, I'd imagine, if I remember correctly. Yeah, here we go, fourth quarter. Oh right, the fourth quarter should be the 10Ks, I forgot. CCG, okay. So essentially this should add up, right? $20,000. Oops. Minus
Oh, that's my students in my class. So the students in the project in the group, we have approximately 25 to 30.
So 8.89. Okay, yeah, that's pretty reasonable. All right. I don't know. They don't give me the sort of segment breakdown though, which is unfortunate. Oh, never mind. Let's go. All right, so 3164 then 5185 495. Okay. Okay, so then let's sum this up. Two 509 3663 473. Let's see what the sum. Yeah. Okay. Thank you. Okay. $487,823. So I think that would probably be Q2 10. Yeah. So I think we could use this one then. So I think 2023 then was kind of this road to recovery in terms of revenue growth. You sort of see this increase. 2024. Okay, so yeah, this does seem very cyclical, where you do where you tend to have lower growth in the early quarters and then higher growth in the later quarters. Q3 tends to be pretty strong for Intel. Okay. Can I get some water real quick? Okay, so 2024 Q3, we're starting to see, yeah, year over year though, doesn't seem terrible. Okay. Oops. Okay, so percent year over year. Alright. So this is 2023 then. Oh, we don't want. Yeah, we want 2022. Okay. Q2 PDF. All right. Item 7. Actually, no. Sorry, this is CCG maybe. Yeah, I'll just scroll through. All right, here we go. Two, 8, 9, 4, 7, 5, 1, 6, 2, 5. Okay. Ooh, I gotta get the operating income for those months too. Okay. Q2. Okay, so 2792 6734 727. Just the sum. 1,253. Okay. And then if you look at, let's say, operating income, then 4029 1085. Yeah, I don't know where this 1400 comes from. So I think Q2, so 2022, this is when, I'm trying to think. I think Raptor Lake. I think it was either Raptor Lake or maybe Alder Lake. 99% sure it's Raptor Lake. So that's the 13th, 14th gen processors that Intel make. They released then. Recently, there's actually some problems with the microcode that showed up with the Intel 13th, 14th gen processors. I think they ended up patching that, but the problem was that you'll get these blue screen type bugs when you're playing games. I think what Intel was doing, what could be that the microcode itself was allocating data to the wrong registers. So that's what the microcode should do. It should be kind of like this data allocator, memory management type tool that is used whenever you're running your processors. So that failed, got patched. Maybe people thought, okay, shit, if Intel is going to make processors that don't work, I might switch over to Intel. Could be a problem. But that's where the Intel Core Ultra series kind of comes in and tries to make sure that you are paying a shit ton of money for great processors. Yeah. Okay, so 4029, right? Let's see. Operating segments, desktop. Two, 641, 5959. Oh. 5959, 694 is equal to sum. So pretty strong revenues, but a lot stronger. Oops. Margins. So year-over-year growth, we take this, divide this by that, subtract 1. Yeah, year-over-year, that shit's tough. Then margins, right? So margins, if we take a look at client computing, so 2827 and 4288. So margins are very strong. So 40%, yeah. It's just, I feel like this is probably where it just starts going to shit. Yeah, they have improved. So this is probably the worst of it. (2021, 2022). That's when you saw margins really take a hit. Yeah. So if revenues fell by 25%, then that leads to a 50% drop in operating margin. That's rough. That's rough. Okay, so I think probably gonna end the stream here. I gotta go use the bathroom real quick, and then gotta go hold some office hours. And then once I'm done with that, probably get something to eat, go to the dining hall, and then set the stream back up again. So thanks for tuning in. Catch you guys in the next one. Peace.